So we're going to start this chapter talking about, in general, chemical bonds. We're going to be looking at a few different types of chemical bonds as we go, but this is just kind of general overview of what they are and why and how they work. So first off, the definition of chemical bonding is the joining of atoms to form a new substance. So we know that a chemical change happens when two or more things combine and you get a new substance. So when those reactions happen, a lot of time chemical bonds are broken and they are formed when they're forming those new things. So the chemical bond themselves are the interactions that hold two atoms together. When we have a chemical bond, the electrons are what makes that happen. We know that our protons and our neutrons are in our nucleus. The electrons are on the outside, and they are what are causing the bond to occur. They will either be given away, they'll be taken from another atom, or they're going to be shared. So that's going to determine what kind of bond that we have. But when this happens, no matter what it is, a lot of energy is going to be used. So energy has to be put in for that to happen, and when bonds are broken, energy is given off. Depending on which bond it is, there's different types. It's going to be stronger than others, so there's going to be more energy put in if it's being made, or more energy given off if it's broken. But we're just going to be going through three different types of bonds, or more than that, but the three most essential basic types of bonds to get you started. Like I said, the electrons in the atom are what cause our bonding. So I want to look at the electrons in the atom, some numbers here, just so we have a good understanding before we start diving into this chemical bond stuff a whole lot. Electrons are negative, protons are positive. Hopefully we've got that down by now. When an atom is neutral, so it does not have a charge, it has the same numbers of electrons and protons. We know the number of protons from the atomic number. So if it's neutral, that means we have the same number of electrons and protons. We had that with the atom model that you guys built. You should have had the same numbers of protons and electrons. We are going to be making diagrams, and some with energy levels. There's a couple different types, and they show our electrons in energy levels. Now, it's not exactly true. They do take on a certain energy level per se, but electrons aren't sitting still in one spot, and they're not just going in a circle. They're flying everywhere, but certain electrons have certain amounts of energy. So when we do those diagrams, just keep in mind the electrons are flying around in the electron cloud. They're not staying in rings like a lot of you had built your atom diagrams with those rings. They do represent an energy level in a sense. It's just not what it actually looks like within an atom. So the valence or electrons are the ones that are doing the bonding. These are the important ones. So these are the outermost energy level electrons. When we do these diagrams, we're going to be drawing different energy levels, and you can see in this circle here, we've got two energy levels represented. The first energy level for all atoms can only hold 2 electrons. We call them shells sometimes, the first shell, second shell, sometimes we'll say level. Either way, it's interchangeable, but the first one can only hold 2 at most. If it has 2 in it, it's a full shell. The rest of the shells past that can hold 8. So it's going to have 8 electrons in order to be a full shell. That is the goal of all atoms, is to be stable. They want a full outer shell. So that is why the valence electrons have anything to do with bonding, is because they want to pair together or give electrons away or take them from others in order to have a full shell and be stable. They pair up as they go through the energy level. They're going to be in pairs. We will talk more about that when we talk about diagrams here in a little bit. So to determine the number of valence electrons in an element, there's a pretty easy trick. But the longhand way would be to just look at the number of electrons there are total in that element. So for example, if oxygen has 8 electrons, we could draw out energy level diagrams to see how many there are left in that last shell. So we could draw the first energy level. Here, let me get a pen. And again, you know how well this goes with my drawing. It's not so hot when I have a mouse pad. So if we have our first energy level, we know there's 8 total electrons because its atomic number is 8 if it's neutral. So we could have 1 electron and then 2 electrons for the first energy level. And then we know we're going to have to go to at least a second electron energy level. So that's a total of 3, 4, 5, 6, and they start to pair up, 7, 8. So that's a total of 8 electrons. So if we count how many are in that last shell, we have 6 total, and that's outside shell. So that means there's 6 valence electrons in oxygen. So it's a long way to do it, but it can definitely get you there. It starts to get, obviously, the higher the atomic number, the more protons and electrons. It gets to the point where it can be a bit of a long job. But there is a trick for the majority of the periodic table, for a large amount. And when we do these problems, I'm only going to give you ones that you can use the trick on. So if you look at the group number, so you should hopefully know that's your columns, that can help you determine how many valence electrons are in that group, or in that element. So oxygen is in group 16. If you look at the second digit, the digit in the ones place is what we're going to be looking at, is a 6, and oxygen has 6 valence electrons. If you look at hydrogen, sodium, potassium, they're in group 1. They all have 1 valence electron. Beryllium, and what else am I going for? I don't know. Other group 2 elements, they all have 2. We skip all those transition metals in between because those transition metals, they're called transition is because they have sometimes a varying amount of valence electrons because they're based on their charge. So we don't use a trick for all those ones in the middle, but if we go to group 13, there's 3 valence electrons, group 14 is 4, and so on and so forth. So group 18 has 8. They have a full shell. That's why they don't react. We've talked about how group 18 doesn't react. It's because they have a full shell of valence electrons. Helium is the only exception there because it only has 2. It only has 2 total electrons. So there is only 2 valence electrons, but it still has a full shell. So it doesn't follow the group trick there, but it has a full shell. So that's why it's in that group. The number of valence electrons is what determines a lot of its characteristics. So that's why all of our families, we know our families have similar traits. So they have similar traits because of these electrons, and they're all grouped together in that way. That's why this group trick works. So if you are listening for some extra credit, I know this is a longer video, go ahead and just draw a star next to the title of this slide or the title of this section on your page so that I know that you are listening. Okay, so an electron dot diagram is something that we are going to be making, working with the next couple of days. It's not too bad if once you know how to determine the number of valence electrons, which I think will be pretty easy as we get going with our group trick. We'll be able to make these, but basically it's just a shorthand version of drawing those Bohr diagrams, which is the energy level diagrams with those rings, because we can get up to some of those really high atomic numbers, and those Bohr diagrams can be huge. But this is a shorthand way to look at the valence electrons to represent bonding. So basically all we have to have is the chemical symbol and to know the number of valence electrons. So if we find the chemical symbol, we write it down. So let's say, and we'll do an example here, but on the next slide. But let's say we have oxygen, we write down an O. Then we find the number of valence electrons, which we just determined was 6. Then we have to draw the electrons around the 4 sides of the chemical symbol until we have used them all up. And one rule is that they want to stay single until they pair up. So I'm going to show you this on the next slide with a drawing. So we have sulfur, and sulfur has 6 valence electrons. It's in the same group as oxygen, group 16. So we know it has 6. So we're going to be drawing all 6 electrons around the symbol, and we're going to be drawing it on 4 different sides. So we go around the letter 1 time completely before we start to pair them up, because I want to stay single as long as I can until they absolutely have to pair up. So if we have 1 electron, and please again forgive the drawing, 2 electrons, 3 electrons, 4 electrons. Now we start pairing them up because all 4 sides are full. 5 electrons and 6 electrons. So that's it. That's your diagram. You just draw it, you pair them up once. If you have more than 4, there's going to be at least 1 pair. You will not pair them up until you have each side full, but you just use your number of valence electrons and your symbol. So we are going to be going through that the next couple of days. Make sure we've got that down, and so hopefully we'll feel comfortable with that.